Okay, so the last time we met, we've been talking about computer organization or computer architecture. We talked about, just as a quick review, simple structures versus complex structures, that computers are, in a sense, a simple system of two states. Basically, it only understands a very few sets of instructions. This binary duality system is used that incorporates the two states both into memory and execution. When instructions are coded and then translated, the two-set system sends this out to the hardware as to execute what it needs. Hardware needs to incorporate the two-state system to fetch instructions from memory and then execute instructions repetitively in a cycle. We talked about what that cycle looks like. The two-state system also needs to represent data in the two-state system, from various things from numbers and booleans all the way up to fancy things like colors and videos. It eventually has to represent data as a two-state system, okay? So the CPU uses the ALU, the CU, and memory. Memory, which is both RAM, ROM, immediate memory or cache memory, all the way to persistent or permanent storage, okay? Basically CPU, ALU, CU, IAS, and then secondary memory. Basically CPU and memory, that's the way you can look at it, okay? The instruction cycle, again, fetch, decode, execute, and store. Fetch in some data from the storage, decode what to do with it, like what do I do with this instruction, execute what it just figured out it needs to do, and then restore any results or the answer back is the cycle that the machine goes through as it runs through your code, okay? When we got into data representation, we talked about, is it just on-off booleans, plus minuses, 0, 1s, binary data? How do we turn that into numbers? We were working on a system for that, okay? Even doubles and characters. Oh, well, they use a lookup table for that, the so-called ASCII table. How do I do a string? Well, a string is just an array of characters. How do I do a class? Well, a class is just an organization of all this primitive data. So all the primitive data turns into a complex piece of data, okay? And all that data is binary. It's all in the two-state system. We talked about this simple 16-number table, how it can be useful to you for coming up with some of these initial patterns of converting numbers into binary digits, okay, into the two-state system. We talked about patterns with this. I'm not going to review all of it, but that it goes 0, 1, 0, 1, 0, 1, then 0, 0, 1, 1, etc., okay? Or that we can count normally just using the numbers ones and zeros. Okay. Then we talked about numbers other than integers, like decimal numbers, and how this can be represented in a polynomial type form, where you could take the 3, the 9, and the 4 and represent them as powers of 10. Or if we switch this and switch the base, we could change the base to base 2, and from this we derived a formula. The formula, by dividing by 2, and remainders are either 1 or 0, will form a pattern to generate the digits and generate binary numbers. So that's where we kind of left off, if you recall, was converting numbers from binary to decimal, etc. Okay. So I also have some slide notes on this, just to review it real quick. So converting from one base to another. Come on. Come on. Okay, so, and again, this was just the stuff we just talked about, that we could represent numbers as polynomials, and polynomials with a base. We're used to base 10. Binary uses base 2, okay? So it's the same system, but in a base 2 system. And when we do the conversions for the things like that, the easiest way to start it off is to memorize this chart, and we talked about ways you can do that. Once you get past the chart, you can then move on from the chart to the formula. And the formula, which the computer's running pretty slow today. The formula, okay, for base conversion is, while the number's not 0, divide the number by 2, obtain the quotient and the remainder. The remainder is the next digit of the result away from the decimal to the left, and replace the number by the quotient. Now, this is a way to look at it. This could also be just translated. I wrote it that way because it looks like pseudocode, because it essentially is, right? You could write an algorithm to do this quite easily. So here's another example. 375 divided by 2, remainder 1. The answer was 187. 187 divided by 2 is 93, remainder 1. 93 divided by 2, 46, remainder 1. 46 divided by 2 is 23, remainder 0, etc. It could go all the way down. When I finally reach a point where a 0 appears here, I stop. The sequence of 1s and 0s formulates the binary number. Okay? Now, going back the other way. Okay? Start with a result of 0. For each digit working left to right, multiply the result by 2 and add that digit. Okay, let's try that. We're going to convert 11010 back to decimal. So we start with a 0, multiply by 2, and add the 1. Okay? This 1 then moves to the next one. So that 1 moves down. 1 times 2 plus 1, that's the next digit, equals 3. The 3 moves down. 3 times 2 plus 0, that's the next digit, equals 6. 6 times 2 plus 1 equals 13. We're now finally up to the last one. 13 times 2 plus 0 is 26. So this number is 26. Okay? You're probably going to want to practice that. You're probably going to want to practice that. We can talk about that later. Okay, now, for hexadecimal numbers. Hexadecimal, which is base 16, also can be done this way, but it's simpler to just use that chart that I showed you to memorize before. Okay? So hexadecimal values use 0 through 9 and A through F in terms of letters. So the method is group 4 binary digits at a time and look it up on the table to figure out what its hexadecimal equivalent is. So here's an example. Here's a binary number. So starting at the point where the decimal would be, I group off 4 digits. Look that up on the lookup table, and I realize that's the number 5. And then I grab the next 4 digits, and I find that's the letter A on the table. That one doesn't have 4 digits, but you can always assume there's leading zeros, and that's 2. So this binary number represents 2A5 in hexadecimal or base 16. Okay? Now, if you're converting to base 10, you can use binary as an intermediate to go in between. Now, what if we want to go the other way? So if I'm given F, 0, 3 as the hexadecimal number, I can look these up on the lookup table, get the binary equivalent, and then if I need to, I could then convert this binary back into base 10. Okay? Again, we should practice that, but I want to kind of move a little quicker through some content today. Okay, so other than numbers, how are data types represented? We've talked about this, but let's see what I have here. So everything is in that two-state system. Okay? So other than numbers, it's going to need bit patterns to represent other things. Okay? So for example, characters are encoded using that lookup chart. Early PCs use an 8-bit or a 1 byte, okay, register length, which allowed for 256 combinations of patterns. So again, if we're using just 8 bits, we have a maximum of 256 patterns from those 8 bits. So for example, if they were going to use an 8-bit lookup table, they would allow for 256 characters, which would cover the alphabet, both capital and lowercase, would cover most of your exclamation points and things like that, and spaces, and still have room for more. Okay? But then if you think, if I'm going to use 1 byte for colors, then I would only have 256 colors available. Okay? Well, that's possible too, if I'm going to use a lookup table for colors. Okay? So then if you go beyond colors to other things that it's going to be represented by, the early PC 8-bit system did absolutely reach a maximum limit. Okay? So what these patterns are depend on the particular meaning that we assign to them, right? So because we had a limited combination, we had to kind of figure out, and that's where tables came from, the pattern connected to meaning. So this pattern of digits represents this letter. That's the meaning. Okay? If we move up to 32-bit or 64-bit pattern recognition, then we have a lot more patterns. But it doesn't matter. Like, we can keep moving up in patterns, right? We can go from 64 to, you know, et cetera, et cetera, et cetera. We can keep expanding that, but it's still going to represent a finite number of patterns that we can represent. So there has to be certain agreements, and that's what was stated. That's what the ASCII table represents. It represents an agreement that this was the rules, and this is an important word for you guys to know. In computer terms, they generally use the word protocol to mean the set of rules that everyone agrees upon. So you're going to hear that word here, that protocol is used for pattern recognition. You're going to hear it when we do networking. When computers communicate with one another, they exchange what are called network protocols, which are, again, the rules. Okay. So ASCII, American Standard Code for Information Interchange, is a set of rules that says if you have a certain number of digits in a certain pattern, it will represent this particular character. We knew that, okay? Using 8 bits is what ASCII was originally designed on, so it really only allowed for about 128, not 256 different characters, because only the first 7 bits were actually used, okay? The final bit, the 8th bit, sometimes called the MSB, or the most significant bit, was what's called a parity bit, or a check bit. Now, we'll learn a little bit more about that later, but the reason a bit was used for parity is for when it was transmitted, it would use that bit to determine whether or not the data was transmitted properly or not. Okay, we'll get more into that later. But even though it originally said 8 bits, it was only using 7 of them. Okay, one of them was being used for transmission checks. Okay, so every time you press a key on the keyboard, it's still using the ASCII binary code system in what's called the basic input-output system, or the BIOS, of the computer. Okay, and there's an example, capital A, which is the decimal number 65, or the binary number right there. Whew, I'm going to pass out today. All right. Now, other characters other than letters are in the ASCII table. So even weird characters like this weird A with a thing over it, or the 0 with a line through it, or this thing, I don't even know what that thing's called. I know it's AE, but... and also some characters that aren't printable, okay? Now, some of these are throwback characters. So some of them are for old sound-based modems. Okay, do you guys know what a modem is? You are old enough to know that, right? Do you know what the word means? It's actually 2 words put together. Mo and dem. Mo stands for modulator, and dem stands for demodulator. That's where the word comes together. To modulate means to turn analog signals into binary, and demodulate is the other way around, right? So modem turned 1s and 0s into a series of sounds. Did any of you guys ever hear those old modems? You know that sound system. So in the ASCII table are some sounds that were important for those modems, like to end the transmission. A certain tone was sent. So in the ASCII table, there are characters in there that we probably won't need anymore, but they're still part of that set, okay? So yeah, there's one there. 7 in decimal, 000001111, was to ring the bell of a receiving teleprinter, okay? That is probably not used that much anymore, but it's still part of that ASCII table. So when they set up those set of rules, those were important at the time. Hardware has changed, but the rules were still set, okay? Now, if they're going to reassign that, that's a big change, right? So reassigning protocols is something that, you know, all the hardware people need to agree upon. If we're talking about internet protocols, then, you know, it gets more and more complicated. Okay. Then there are codes like acknowledge and end of transmission. So now let's move up. What about graphics? How do we represent graphics? Well, if you think about it, there are really only 2 types of graphics on the computer, okay? What are called bitmap, or sometimes called raster graphics. Bitmap is a better way to represent it because it relates to what we were just talking about. If we take the first part of that bit, we're talking about 1s and 0s. Then when we talk about map, what we're talking about is, like you'd see when you open a map on a computer, it's a way to present things geographically. And then we have what are called vector graphics. Now, those of you who've studied physics or math know what a vector is. What's a vector? Yeah, it's magnitude and direction. Or more simply, it's a calculation, right? So graphics that can be basically mapped out and graphics that can be calculated is the way it looks at it. Okay, so bitmap images, the computer just divides the picture up into a map, a grid. Each little pixel, which stands for picture element, that's where the word comes from, is what is mapped on the graphic. These raster graphics, or bitmap or raw graphics, then represent what's going there. So then at each little spot, each little pixel, all it needs to know is what color do I draw right there. Okay? That's why if you ever see these pictures that you expand off the internet and they get pixelated, you see the squares. You actually see the colors. So at its simplest level, you'd need 1 bit per square, 1 or 0. And you could represent those as colors like black and white. Okay? So if you had a 10 by 10 grid filled with 1s and 0s, you could represent a black and white image in that map. Okay? Sometimes we're going to need more bits than that, though. If we're going to expand into colors, we're going to need more than 1 bit there. We're going to need to represent all the different colors at each spot. Okay? The number of bits needed per pixel is known as the pixel depth. So this way you can think of it more like a 3-dimensional graphic. So we'll take all the way back to what I'm going to do with the grade 11s in a few minutes. Okay? So let's draw a grid. That was bad. Okay? So can someone count the columns for me? How many columns was it? Thanks. 5. And how many rows? 6. Thank you. Holy moly, you guys are definitely on spring break. All right, so this is a 6 by 5 or 5 by 6 grid. In each spot, I can put a color. Let's say I made this a blue, green, red, black, or leave it white picture. So how many colors? 1, 2, 3, 4, 5 different colors. Okay? So I have 5 different colors that I can use at each spot in there. Okay? So if you think of this as an array as well, it'd be an array at each spot. So that's what I mean by it's a 3-dimensional graphic, right? Think of this like going back, like this. 5 going back. So it's a cube, right? So then you go to each spot on the map and you say which color needs to go there. So watch as I can quickly draw a graphic here. I can just quickly. Okay, there. I drew a graphic, right? It's like a sad face or something. I don't know. But you get the idea what's going on there. So when it stores this, how would it store it? Okay? Okay, so whoops. So let's think about how it would store this to represent this graphic. So one thing it's going to need to know is how many colors. So it's going to remember that there are 5 colors. What else is it going to need to know? It's going to need to know the dimensions of the grid. So it's going to know it's a 6 by 5. 5 colors, 6 by 5. Then what? Then it's going to need to know each individual pixel, what color's there. So if I number these, 0, 1, 2, 3, and 4, it would go, oh, okay. So the first spot, spot 0, 0, would be a 4. Because it's a white spot, right? Then I'd go to spot 0, 1. Oh, that's also a 4. Okay? So remember, think about what this means. This is the depth, how many colors I need. This represents the height, and this represents the width of this graphic. Okay? Then I just start funneling in all the data. Then I get to spot 0, 2, right there, right? And what would that be? Well, that would be a 0. and then a 4, and then a 4. But you can see this would just keep going. Then I just go to the next row, right? And then I'd go, oh, okay, then a 4, then a 0, then a 4, then a 0, then a 4. Then what's next? You guys tell me. Then a 0, then a 1, then a 4, etc. Okay? Now remember, each of these digits would also be represented in binary. Okay? But what if these two numbers got screwed up? Right? If I stored them opposite, I would draw a different graphic, wouldn't I? So in order for me to know that, I need to have set of rules or protocols saying this, so that width or height comes before width or width comes before height. Doesn't matter as long as I agree upon the rules. You're right. It would be basically one big array, or it's basically just one big binary number, right? That's all it really is. It's just one big binary two-state system to represent that. As long as you know when it began and end, and as long as you knew the protocols, you would be able to reproduce that graphic. Okay? The deeper the color depth, if I go to 16 million colors, they got a bigger color depth, right? For that, maybe I shouldn't represent it as 16 million lookup table things. Maybe I use something like a red, green, blue to mix the colors together. And we already know some of the way that code that happens. Okay, now, let's say that happens. Okay? This would be stored, this whole thing would be then stored as a bitmap graphic. Okay? But you guys probably know most graphics on the internet, for example, are not bitmap graphics. They are converted into a different type of graphic. So we'll talk more about that in a second. All right, so that's pixel depth. Okay? 1 bit per pixel would be a black and white image. The greater the range, the higher the pixel depth. For example, a picture that uses 24 bits per pixel can contain up to 16.7 million colors, which, by the way, is ridiculous because the human eye cannot detect that many colors. There are more colors than the human eye can actually detect. The more colors, the greater the pixel depth, but the greater the pixel depth, the bigger the file size. Then we look at vector graphics, which, as I said, are calculations. So they are made up from objects, not from maps. The objects are stored as the mathematical calculation for drawing that object. So an example would be something like this, the letter A. You could actually measure that and get all the calculations necessary to draw that A. Right? Like you could measure the height, the width, everything. Okay? Then to make the A bigger or smaller, all you have to do is plug new numbers into your formula, and the A gets bigger and smaller. That's actually way more efficient, because if you think about it, if I was going to use a map for this, I would need a map for that size, a map for that size, a map for every single size. Which is why fonts, for example, are not stored as mapped out fonts. They are stored as calculations for each letter, so that when you change size, you just plug new numbers into the calculation, because computers are good at doing calculations, including things like the curvatures and stuff. All of that is taken into account. Okay? So on a more simple level, okay, as you just look at something like a box, if I just remember those 3 numbers, remember that it's a cube, and then a little bit of numbers for the color, that's going to store a lot less than a bitmap. So now here's the question. Why isn't every graphic a vector graphic then? It takes up a lot of storage. Well, it actually takes less. This would take a lot less storage. Why do you think, Liam? Okay, so what would be an example of a graphic that would be too hard to calculate in terms of the measurements? Yeah, a photo of your face. Imagine I gave you that assignment. Calculate every single calculation to redraw your face at a different size perfectly. Okay? That would be too much. At that point, the calculations would take up more size, like you say, Hayden, so vector graphics can be used for simple things like fonts. Can you give me an example of something else that uses vector graphics? Yeah, shapes like this. I know you've heard of it before. clip art. You guys ever seen clip art in things like Microsoft Word and PowerPoint? There's those very simple cartoon graphics. You notice that when you stretch them out, they still look really good. That's because they're storing them as calculations. And the software takes care of all the worrisome stuff for you. So let me just wrap up today with this. Here's a vector versus a raster. Okay? You will see the pixelation, especially when you enhance, right, or zoom in. The vector graphic just recalculates where the bitmap starts to show the map. You knew that all the way back when you first got on the internet, that you saw that happening, but that's why it's happening that way. Okay, so vector graphics are cleaner, but obviously sometimes actual graphics are too complex to be stored as a vector. But what if they are still bitmaps? Then we can use what's called compression software on the graphic. So let me jump back to here. So imagine this was actually a much bigger graphic than just that one. Okay? So let's imagine that I'm not going to draw the graphic. Whoops. Whoops, oops. Okay, here we go. But let's say it was stored like this, that it uses 256 colors. It's a 1024 by 768 graphic. And then it starts in with all the patterns, right? So the first is a 0, then a 0, then a 0, then a 421, then a 0, then a 0, then a 0, then a 0, then a 428, then a 673, then a 5, then a 0, etc. You get the idea? What compression software does is it starts looking for patterns. So let's say then it had a 47, and then there was 220 zeros at that point. Wouldn't it be easier to store 220 times 0 right there? Absolutely it would. So what compression software does is it starts looking for patterns in the bits and making the patterns more collective. It what's called tokenizes this thing, and it looks for patterns, and it goes, oh, look it, I got a bunch of zeros in a row here. Or maybe it even gets more fancy than that. It goes, oh, look, I've got things with 4s in them, right? I can make those into patterns. So compression software starts really analyzing stuff into patterns. And how deeply it does that is how deeply it compresses it. When you do compression, though, sometimes you will end up losing some of the bits, or some of the stuff gets a little bit tainted, which is what you know when you convert something to a JPEG, you often sacrifice a little bit of the quality in doing so. But that's what essentially compression software does. Compression software, okay, it uses algorithms to shrink the file size by looking for patterns. JPEG, I'm not going to say it to start a war, the GIF graphic, let's just use what it stands for, graphics interchange format. That's what the acronym stands for. Just like JPG should be JPEG, Joint Photograph Experts Group. Okay? Basically takes a bunch of data. Here's my amazing graphic. Compresses it. Do you guys even know what that is? It's a vice, yeah. All right. Okay, the rest of this basically describes what I drew on the board, that the file header keeps track of that important set of protocols, and then a signature in the header to tell you what kind of graphic it is, for example, bitmap, so it's identified in that way. Then things like width and height and pixel depth, okay? So bitmap is coming, there's the width, there's the height, there's the colors, that's the end of the header section of the graphic. Then all the patterns start coming out, pattern, 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 whoops. And from that it could redraw the graphic, okay? That's all set up in the protocols, like I said. Okay? Color require more information. 8 bits moves up to go to 256 colors. We need, okay, I can't even read all this. I'm just too lost here. I think I want to wrap up there because I know the other group is waiting to go. Just want to quickly see. 24-bit, 3 bytes I talked about before, or true color. The bytes determine the pixel depth, and that determines the file size, etc. And then that eventually gets fed into the hardware. We can get into that later. Okay? All right, so I think I'm going to stop there for today.